Hello everybody, my name is Zujany Salazar. I'm currently working as a research engineer in Montimage, and I'm here to present you 5Greplay, a 5G network traffic fuzzer and its application to perform attack injection. This is a joint work with Huu Nghia Nguyen, Wissam Mallouli, Cavalli, and Edgardo Montes De Oca from Montimage in France. Our idea with this work was to give to the open source community a tool that was able to implement security test cases that are very proposed in the literature, but that we found weren't that easy to implement with the current available open source solutions. So the outline of this presentation will be a short introduction about security testing in 5G, then a background about the fuzzing operators that our tool implements. Then we will see the main architecture of our tool, followed by the experimental evaluation that consists in 3 experiments to evaluate specific capabilities of 5Greplay, and we will end this presentation with some conclusions on future works. 5G networks aims to achieve numerous KPIs in terms of latency, availability, bandwidth, energy consumption, etc. And all of these will be possible thanks to the 5G key-enabled technologies. The main examples are the software-defined networks, the network function virtualization, the mobile edge computing, and the network slicing. But all these new technologies will be required to be tested from a functional and non-functional point of view. And in terms of security, we'll introduce new cybersecurity threats. In many cases, some of the previously adopted security and privacy mechanisms will become ineffective or simply not applicable due to the new architecture. So it is necessary the creation of a new set of cybersecurity test cases and tools that will be able to implement it, specifically targeting 5G security concerns. Previous works done by standardization organisms such as ENISA or 3GPP, as well as academic research and industrial reports, has published a collection of the threats and vulnerabilities of 5G. Moreover, the 3GPP has published a wide catalog with security test cases in order to verify if these vulnerabilities are present in the different 5G network functions. The problem we see is that with the current available open source solutions that can modify network traffic, for example, the library of Python SCAPI or TCP Replay, these test cases proposed by the 3GPP and some of attacks reported in the literature are not that easy to implement. This is because these tools are not specifically targeting 5G networks, and they're required to be modified and extended in order to parse 5G network protocols and to be able to modify these packets. This is where we introduce 5Greplay, an open source solution that aims to perform fuzzing testing in 5G networks by allowing to forward network packets from one network interface to another with or without modifications. This tool is already available in our website. Let's check the fuzzing operators in which our tool relies. 5Greplay, in order to modify network packets that can come from a picket file or from a specific real-time flow of network packets, relies in the following fuzzing operators. The tool can delete a packet, can change a specific attribute of a message header, for example, the IP address of some specific attribute of 5G network protocols, could be able to exchange the order of 2 consecutive packets and duplicate a specific packet. All of these atomic operators can be used individually or combined in order to perform less or more complex fuzzing scenarios. in order to test, for example, via virtual network function of 5G, intrusion detection system targeting 5G or 5G applications. Let's see how this works in the architecture of 5G replay. As I already mentioned, the input of 5G replay can come from a PCAT file or from an online, or can be online traffic coming from a network interface. First of all, the tool will filter the incoming packets based on rules defined by the users. In these rules, the users first would define how to filter the packets. This could be based on its IP address, for example, or based in another attributes of the packets. Also, the user would define in the rules what action it desired to take with the packets. This could be a modification or simply dropping this packet. Later, the tool will take the packets that weren't filtered and we make an action that the user also defined in a configuration file. This can be dropping the packets that weren't filtered in the first place or forward them together with the modifying packets into the output network interface that will be the system under test. That again can be a virtual network function of 5G, a 5G intrusion detection system, etc. Let's pass to the experimental evaluation we perform. The first scenario has the objective of create and send malformed packets into 5G core networks. In this case, we use the simulators Free 5GC and Open 5GS. And we designed rules of 5G replay that could filter the NGAP traffic sent between the user equipment and the AMF of the simulators and modify them in order to change its protocol identifier from 60 to 0 and reinject them into the core network. This with the objective of testing the robustness of these 5G core simulators against unexpected entries. As a result, we got that Free 5GC show us an alarm, a warning, saying these packets are NGAP malformed packets because the protocol identifying is different from 60. So the simulator dropped the packets and continue working normally, and we conclude that the simulator passed this test. Nevertheless, Open 5GS was not able to handle this packet, as we can see in the picture, the simulator crashed, and we conclude it failed this test. And regarding 5G replay, that was the main target of our experiment, we conclude that it was able to replay and modify 5G network packets in an online way by using the Fuzzer operator change attribute, and the network traffic and its output, the output of 5G replay, was accepted by the open source simulators. The second scenario consists in performing a security test cases already proposed by the 3GPP. In this case, the 3GPP proposes a test case to verify if an AMF is protected against replace attacks of the security mode complete of the NGAP protocol. So again, we implement a rule of 5G replay that filtered the security mode complete messages and reinjecting into the core network. In this case, we performed this test against Free 5GC, and we could conclude that the simulator was protected against this kind of replay attack because we got the following warnings, where the AMF simply tell us that the replaying message are not part of any user equipment context, so the simulator dropped them and continue working normally. Regarding 5G replay, we could be able to prove that that the tool was able to perform at least this type of security test proposed by the 3GPP. The last scenario was a hand bandwidth traffic generator. In this case, the objective was to test the scalability of 5G replay and to perform a stress testing or a denial of service attacks against the Open 5GS and Free 5GC. As a result, we got that Open 5GS crashed when we sent more than 1,780 packets with a rate of 509 packets per second, while Free 5GC crashed when we sent over 3,000 packets with a rate of 594 packets per second. To perform this scenario, we configured 5G replay in order to range it or replay all the traffic between the user equipment and the AMF into the AMF. And we could conclude that 5G replay can be used to test the robustness of 5G core services by relying in the fuzzing operator duplication packets. Let's pass to the conclusions. We present 5G replay, a tool that we proved to be able to receive online and offline entries, to systematically create and send malformed packets that were accepted by 5G open source simulators. And also we proved its capability to evaluate the robustness against unexpected entries of a target, to perform security test cases proposed by the standardization organisms such as the 3GPP, and to perform stress testing into a target. For future works, we're planning to define new 5G attacks that can be performed by the tool, new techniques to manage encrypted traffic, to implement and test new ways to alter packets. This is new fuzzing operators, and to extend our experimental evaluation into another 5G interface, because in this case, we were only targeting the M2 interface. This research is supported by two European projects that we would like to thank: Sanko's project and Inspire 5G+. Thank you all for your attention, and I hope to see you in the Q&A sessions to listen your questions and comments. Thanks a lot.